Hey everybody, welcome to Module 3 of NT160. We're going to be talking about reactor water chemistry, water in a reactor. And so these are only talking about light water reactors, which are all the current commercial boiling water reactors and pressurized water reactors in the U.S. Water transfers heat, moderates neutrons. In our light water reactors, it stays in direct contact with the fuel, the piping, the pumps, all the structural materials. So water chemistry, what the pH is, what chemicals are in it, all that affects corrosion, contamination, fuel integrity. And then because of this thing we talked about, radiolysis, it affects radiation fields. It affects how much radiation is in the steam piping and the secondary piping for PWR. And overall, so that all plays into, of course, reliability. It's one thing we're always worried about after safety. Worried about safety first. So if we get out of control on chemistry, if we lose track of pH, if we allow contaminants to get into the water, then we get corrosion. We get deposits build up. We get higher dose rates. We get fuel problems. I should be writing while I'm talking. Let me set that up here. So water matters because first thing it does for us is it transfers heat. That's why we have whole purpose of having a reactor in the first place. It moderates neutrons 1 over 0, right? It takes fast neutrons and makes them thermal neutrons. And then it touches touches fuel and metals. It is in constant contact, and through that, it can affect fuel and other components. Going to end up writing into my face, aren't I? Why? Well, one of our biggest concerns is corrosion. Yeah. So overall, all these things affect safety. So our goal is keep the water clean. We have all these demineralizers and filters, keep the pH under control, keep the chemistry under control. We add things we'll talk about like hydrogen in a boiling water reactor, and noble metals, and in a pressurized water reactor, we add things like lithium hydroxide, ammonium, boron, boric acid. So we have to keep all these things in control to minimize corrosion, because what we're trying to protect here, the main thing we're trying to protect is the fuel, because if any corrosion starts affecting the fuel cladding under the conditions in a reactor, the high temperature, high pressure, the corrosion can exacerbate really quickly and become a bigger problem, and eventually allow fission products to be released into the coolant, and it just goes down from there. All right, let's step back and look at just the water. Why is water so useful in the first place? Because we have these new high-temperature gas reactors that are using helium as a coolant. Why are they using helium? Why aren't they using water? Why didn't we use helium in the first place with our BWRs and PWRs? So let's look at why water is important. As we learned in a previous module, the water is a polar molecule. So the molecule overall has a slightly negative side and a slightly positive side. So that polarity leads to hydrogen bonding. Hydrogen bonding is what gives water the properties that we see: the cohesion, the adhesion, the surface tension. And it also has a high specific heat, which makes it effective as a coolant. So it can absorb large amounts of heat without changing temperature too quickly. Also, because of the oxygen atom, water acts as a moderator. So a neutron comes in, smacks into the hydrogen, the oxygen. It transfers a lot of its energy and slows it down so that the chain reaction can continue. So the reason it works is because of its polarity. It's hydrogen bonding, H2 bonding. It's high specific heat, and it's moderation, especially its moderation. What you'll find in these new high temperature gas reactors that we're going to be talking about, graphite is also an effective moderator. But let's move into the chemistry idea, the core The basic thing we're talking about is radiolysis. As reactor coolant passes through the core, it's exposed to intense radiation. There's a lot of radiation. There's a lot of neutron bombardment. There's a lot of gamma, high energy electrons. There's lots of other energetic particles. There's lots of stuff going on inside a reactor, right? When radiation interacts with water, when radiation, so like a gamma, bad gamma, let's try it again. Gamma interacts with water, H2O, it ionizes the water and breaks that chemical bond. And so you end up with hydrogen and oxygen, but not directly. So it's a process called radiologic decomposition. Okay. The first step produces highly reactive species, so an ion pair, which includes a free electron and a positively charged water-related ion. From there, the chemistry takes off. A short-lived intermediate species. Species is just variations, right? And some of them are short-lived, some of them are intermediate, some of them are long-lived, and a lot of them are highly reactive. So H3O plus, and then we get our OH, our hydroxyl radical. We get our hydrogen atom. Oh, it's just H, hydrogen atom. H2 is the molecule. And then we get OH minus, and that's hydroxide. And then we get our hydrogen peroxide. So it goes through all these things. This is like the chemical decomposition of water in radiolysis. And the one that matters most is the hydroxyl. That hydroxyl is a free radical that has an unpaired electron. So it's very, very reactive. In reactor systems, those reactive species drive oxidation. And oxidation is corrosion. So the easier way to remember this is radiation breaks water down and it produces hydrogen oxygen. Like we know that, but there's a lot of these intermediary steps along the way. It produces hydrogen peroxide, it produces these other reactive oxygen species, and all those things matter because the oxygen and the peroxide increase corrosion risk, and hydrogen plus oxygen can create gas management issues. So one reaction worth remembering is that hydroxyl radicals can combine to form hydrogen peroxide. Hydrogen peroxide, this one down here, is an oxidizer. That means it can make the coolant more aggressive towards materials. All right. Now, if radiolysis is breaking the water down, why doesn't the system just keep filling up with hydrogen and oxygen forever, right? Why isn't it just a hydrogen producer and an oxygen producer? So the answer is that we keep the reactor coolant in a closed pressurized system. For a boiling water reactor at about 1,000 pounds, and for a pressurized water reactor at about 2,000 pounds. So in that kind of a system, we have radiation doing two things. It's fighting with itself. Radiation drives the decomposition, but it also drives recombination. So water's being broken apart, but the products are also being pushed back towards water. So we get this weird dynamic equilibrium. We get decomposition, we get recombination, and then that's the whole thing is a balanced equilibrium. So it's not static. It's not a static system. Radiation's constantly pushing the chemistry one way and then back the other. So let's shift over and talk about pressurized water chemistry control. In a pressurized water reactor, the goal is to suppress oxygen and reduce corrosion. So we keep the coolant in a desired pH range, and we keep dissolved oxygen extremely low. To do that, we add a little bit of hydrogen. Excess hydrogen shifts the chemistry away from the free oxygen and back towards water. So it helps keep the radiologic decomposition suppressed. It helps keep the water production going. It helps keep things from forming all these radicals. The hydrogen basically scavenges the oxygen and suppresses the oxidative side of the radiolysis, and so that reduces corrosion risk. In your briefing sheet, it also identifies lithium hydroxide as the pH control chemical in the PWR, and boric acid as the reactivity control chemical. So, and that can be a little different depending on the plant. Like in the Navy, we never added lithium hydroxide, and our reactors on the submarine were pressurized water reactors. We added ammonia. And so in I think it's in your student text, you'll find it talks about ammonia. And in your briefing sheet, it talks about lithium hydroxide. So for PWR chemistry, there's several things we add. Boric acid, boron. We add boron for reactivity. So in a BWR, we control power, the power of the reactor, the neutron flux, with control rods. And we do that in a PWR as well. We raise and lower control rods, but we try to minimize moving control rods in both of them. So on a BWR, we also change the flow rate of the water through the reactor, and that changes the size of the bubbles, the voids, right? Less flow is larger voids, suppresses the moderation, right? Because you have less moderation, so the power goes down. So less flow, power goes down. And then if you increase the flow, you get more power out of a BWR. In a PWR, we can't change the power with flow, but we want a second way to control power under normal conditions to fine-tune it. We don't want to fine-tune it with control rods all the time for nuclear physicist reasons. Means I don't know. We want an easier, simpler way. So for PWR, what we use is boron. We actually inject boron in the form of boric acid into the coolant, and that's for reactivity. We also inject lithium hydroxide. Lithium hydroxide's for the pH. What else do we add? We add hydrogen. And we do that to reduce oxygen. Yeah. So that's the PWR chemistry. So what happens when air gets in? Air brings in oxygen and nitrogen, right? The major reactions between the oxygen and the dissolved hydrogen. If we add enough hydrogen, and there's been some radiologic decomposition and the oxygen is built up, then the oxygen is consumed and the system stays copacetic, right? But if enough air gets in, then we can deplete that hydrogen inventory, that excess hydrogen that we've been adding, and then the chemistry shifts. So under radiation, hydrogen and nitrogen, and this is another reason, another source of ammonia. Hydrogen and nitrogen form ammonia. Ammonia and water can make the coolant mildly basic, right? We're talking about pH. You got acidic and you got basic. Yeah, but if hydrogen's depleted and oxygen stays, oxygen and nitrogen form nitric oxide and nitric acid. The nitric acid drives the coolant acidic. And that's a bad direction. We would prefer to have it slightly basic than slightly acidic. So the low pH increases corrosion and can destabilize the protective oxide films. We do feed and bleed to help reduce that concentration. And like on submarines, we would add ammonia to help shift that. So if we get air in leakage, the oxygen reacts first. A small leak is manageable. A large leak uses up our hydrogen inventory. We possibly get nitric acid formation, and that's bad. So, yeah. All right. Let's get back to the water and something else that happens with it through these activation reactions. Water can become radioactive. One of the most important examples is nitrogen 16. So you have oxygen 16, which which produces nitrogen-16. And nitrogen-16 is a major dose contributor, which means, I'm working at a boiling water reactor and I'm going up on the turbine deck. They have to put boundaries. Radiation protection technicians have to do surveys and put boundaries around it at operation, because those nitrogen-16 gammas coming into the turbine off the steam line out of the reactor are producing a lot of radiation. And so, yeah, that activated coolant leaves the core, moves through the piping, and it has a decay. I should have looked that up before this, like 7 seconds. Yeah, I'm pretty confident in that. 7-ish seconds. But that steam's flowing fast. So it gets all the way to the turbine, and you get that short-lived nitrogen-16 dosing outside of the reactor, outside of the primary containment. And so it moves through the piping before it decays, and there's other short-lived activation products. There's tritium formed from deuterium. Tritium's different because it has a longer half-life. It's mostly a concern if as an internal hazard, if it's inhaled, ingested, or absorbed. So activated water products, this is an easy one, nitrogen-16, other stuff, tritium. If I say other stuff, then obviously I'm not going to quiz you on all the specific stuff, right? These are the ones we're worried about, mostly nitrogen-16. We're not super worried about the tritium right now. The big idea is that water can become radioactive. It can increase dose, and it's a big contributor to dose during operation. So what parameters do technicians and operators pay attention to in the plant? What are we worried about, right? We worry about pH. We've talked about that already. We worry about dissolved oxygen levels, right? We want to make sure that those are minimized. We worry about our hydrogen levels. We want to make sure that there's an inventory of hydrogen that's building up to minimize the oxygen. And then we want to worry about the total gas, because it's like if there's air in leakage, then we also get nitrogen and other gases. So TG is total gas, and we worry about conductivity, right? Pure water by itself with no ions in it, nothing in it to transfer electricity, doesn't have a lot of conductivity. But if you start adding things to it, conductivity goes up. So measuring conductivity is an indicator of, do we have anything in the water that we don't want? We also monitor chlorides. We monitor fluorides. We monitor boron. I'm running out of room. Boron. Radioactivity, the fuel condition. We have cleanup systems. We monitor our cleanup systems too. But these are some of the parameters, like especially if you're a chemist at a nuclear power plant. All right, so let's start with pH. Low pH strips the protective films and increases corrosion. So slightly basic conditions are slightly preferred, basic being above 7. If we want a slightly higher, and not much, we're not talking about very much, because incredibly basic is also bad. The dissolved oxygen is the corrosion driver, right? This is the thing we want to minimize. We want to get rid of all the oxygen as much as possible. And so hydrogen matters because this is what keeps the oxygen in check. It's what consumes the oxygen. Total gas matters because dissolved gases come out of solution and they form gas pockets. And those gas pockets build up in the pumps. We have pumps in both PWRs and BWRs, and these gas pockets will collect and damage the pumps. It leads to erosion, which creates corrosion products, which can get activated, cavitation, loss. Conductivity, like conductivity is a measure of that. Like if we start damaging a pump and those products go through the coolant, and then conductivity goes up, and it's a useful indicator. It tells us whether we have ionic contamination. It doesn't tell us which ion. It doesn't matter which ion. We just know something's wrong, and that's what matters. So And then chloride. Chlorides are important specifically because of a specific type of corrosion that we especially worry about in nuclear power plants, stress corrosion risk. Fluorides matter because the fluorides damage the zircaloy cladding on the fuel. And then if we damage the zircaloy cladding, we get radiological problems. And then, of course, boron is an PWR and provides part of our reactivity control. So in a BWR, your material says that there's no boron in normal operation. I want to point out, we do have boron, what we call slick tanks, the standby liquid control tanks that are full of boron solution, borated water, and we can inject those in a BWR. We just don't unless there's an emergency. So when we try and scram the reactor on a BWR, we have our logic buttons, and we push those logic buttons and the rod go in. What if they don't? Well, we have a mode switch, and we rotate that mode switch, and it's an informal backup reactor protection. We rotate the mode switch. Rods don't go in, or should go in. What if they don't? We have a backup scram, and so we push the alternate or backup scram valves, and we hopefully put the rods on. What if they don't? What if all our methods of trying to get the control rods in to shut down the reactor don't work? We inject boron. We start these boron pumps. It fires a couple of explosive valves and injects boron into the reactor. And it injects enough boron that at 100, if we're cruising along at 100% power, all the control rods completely out, we can shut down the reactor. So PWR chemistry, we normally use a little boron, and we use that to regulate the power of the reactor. It's reactivity control. We use lithium hydroxide for pH. We use hydrogen for oxygen suppression. Whereas for a BWR, we don't use boron. We do add hydrogen, and noble metals. What noble metal is added depends on the power plant. I know at some plants they use platinum. They can use some noble metals that are not reactive that help plate out and protect the system. So, for example, platinum. You can plate it out with platinum. So PWR, we have boric acid, we have lithium hydroxide for pH, and we add hydrogen. So hydrogen is to minimize the oxygen, lithium hydroxide is for pH, and boric acid is for reactivity. Whereas in a BWR, we have hydrogen. We don't add boron, and then we use noble metals. And we just say noble metals because there's a bunch of them we could use. It doesn't matter which one. All right, so what do abnormal chemistry conditions look like? So some of these parameters start affecting each other. If air enters a system, depletes the oxygen, the pH can go low. It can start going acidic. That weakens the corrosion films. They release into the coolant and triggers what we call a crud burst. You get a bunch of corrosion products in the coolant. This crud burst is a sudden release of corrosion products into the coolant. When that happens, they become activated. They travel through the core, they get activated, and radiation levels go up. And when radiation levels go up, but also conductivity goes up, the ion exchanger performance starts to look stressed, right? And so another thing that can happen is you get area leakage. You get hydrogen goes down if you get area leakage. pH goes down. You get a crud burst. You get radiation goes up, and conductivity. And this is all if you get area leakage. So what's another thing? Another abnormal condition is a fuel element failure. So a fuel element failure is where you have like we've talked about a couple of the things that affect the cladding, affects the zircaloy. So if I've got the fuel pellets in here all stacked up, I'm just drawing them with spaces, but they're stacked up. And this is the zircaloy cladding, and then this is the coolant traveling through here. And we get some corrosion, and this blisters, bubbles, and then the corrosion starts and it eats through. And maybe this pellet here has some fission products on the side that have released into the helium inside the fuel pin, and then now it has a path to get out. So now we can leak gaseous fission products into the coolant. So what's another one? Ion exchanger failure. So we have ion exchangers, demineralizers and ion exchangers, demineralizers on the secondary side, on the feed water side usually. And on the primary side, we have ion exchangers with resin in them. And if it overheats and decomposes, it can release all this stuff that it's been cleaning out back into the coolant. So what is overheats? It only takes 140 degrees Fahrenheit for an ion exchanger to be endangered. That's it, 140 degrees. So we try and cool it down to keep it below 140 degrees. Overall, the chemistry, the plant materials, and the chemistry going on, like chemistry's not passive, right? Radiation changes it. The plant materials react to it. Our chemistry control decides whether we have a film of protective layer in there, or we have a corrosive system that takes that protective layer away. So our plant technicians, our chemistry operators, our operators, we watch pH, we watch oxygen, we pay attention to our hydrogen levels. We purposely inject hydrogen. Total gas, we worry about total gas. We worry about conductivity, chlorides, fluorides, for PWR, boron. And then we, of course, monitor our radiation levels, because all of those things tell us what's going on in the coolant. We don't have just a window that says, okay, let me see what's going on with the coolant, right? These are things we have to monitor on the side. So if you understand radiolysis, hydrogen control, oxygen control, and the meaning of these major chemistry parameters, then that's a lot of what you need to know for chemistry. What are we even going to teach the rest of the modules? I don't know. This is a lot. We covered a lot of good stuff here today. All right. I'd like some feedback on this quiz format. This is something I want to try and do. I want to try and do one of these lecture videos every module. I've been meaning to for a while, and I hadn't gotten around to it, and I'm forcing myself to do it. And I think this works. But I'd like some feedback. I'd like your opinion. All right. See you next week.